This video is part of a course on food physics. Here we are talking about microwave heating and fundamentals of microwave heating, to be specific, and that's in two parts. Part 1 has to do with the electromagnetics of microwave heating, and that part 1 is in 6 sections, of which this is the last or the 6th section, discussing oven factors in microwave absorption. Again, it's part 1.6, talking about oven factors in microwave absorption. Here we show the other videos in this series. Before we discuss oven factors in microwave absorption, we had a video introducing microwaves, another one talking about how microwave propagates in a simple geometry. Then we talked about energy absorption and food properties, food dielectric properties, and we talked about waves, microwave fields inside an oven, what's it look like, and then we talked about food factors in absorption. So these 5 are separate videos earlier in this series. We will talk about 3 oven factors. First one, we'll talk about the location in the oven. How does does heating rates vary as we place it in different locations in the oven? The other 2 are how the turntable can make a difference in the heating rates, and how power cycling affects the heating rate. Now, of course, there are other factors. For example, if the oven power itself is higher, the heating rates are going to be higher. We're not talking about that one. So we chose these 3 that seem to be something that we have control on, and they have also interesting physics related to them. As you can expect, a generalization of the effect of placement of food in many different ovens is difficult, and to my knowledge, this has not been done in any comprehensive way. So here is an attempt to try to answer this placement effect inside the oven by doing an electromagnetic simulation of a oven food system, the details of which you can see in this research paper. But it's from that electromagnetic simulation we are trying to show what are the placement effect, little details about the simulation. And so it is for the properties of potato and their spheres of this radius, 4 centimeter radius, and what is plotted here is heating potential. And let me explain that. Heating potential has to do with power deposition. So let me put this sphere, and at any radius, let's say r, we have variation in power deposition at the same radius if we move in, let's say, theta direction or the phi direction, the other 2 directions. At the same radius, power deposition is going to vary. So we're going to average all of those along theta and phi direction at one radius. So it's like we are going to average over all of the uh, power deposition at radius r, and that's what is this heating potential that is plotted here, but it's also normalized by the maximum value, so it only goes up to 1. So it is this heating potential at radius r is plotted versus the radial distance all the way to the uh, the the radius of the sphere, and it is done for 3 separate placements inside the oven, and the exact details of these placements can be seen in this research paper. So this normalized heating potential changes only slightly as you move from one location to the other. Note that this normalized heating potential is an average over all locations at the same radius. Now, the actual values at different locations over the same radius, they do vary from one place to the other, but averaged out at that radius seem to not vary as much from one location to the other. The same was seen for a smaller diameter of half a centimeter. That is, whatever is the pattern, the average value at the same radius does not change with location in the oven. So a conjecture from this study was that qualitative pattern is not changing with position in the oven. The point that we can use perhaps, if I may generalize, that the placement of the food may not be as critical a factor. Placement of the food inside the oven may not be as critical a factor as factors like dielectric property and size. Next, the turntable and how it improves the uniformity of heating. Microwave fields inside a microwave oven are fundamentally non-uniform. So this was mentioned earlier in detail, but here is again a picture of the same. So what we have here is a microwave oven. It doesn't look like the home oven because it is not, but it is still a larger microwave oven that has the same parts with the food placed inside the oven. So if we look at the fields inside this oven, it looks like this, a very non-uniform, and you can see kind of see the highs and lows. So the reds are the highest, and then the blues are the lowest, and you can see these patterns. So they come from the standing wave pattern of the microwave fields inside the oven. So there are places with much higher values of electric field. So foods at that placed at that location would heat lot faster, and then foods at some blue locations would see much lower electric field and would heat a lot slower. So this fundamental non-uniformity is built into the microwave oven due to the standing wave pattern. If I take a section, like this here through the oven, then it looks like this here. So here is the food placed, and you can see these standing wave patterns that shows quite a bit of non-uniformity between here and here, the red and the green and the blue. So if I place the food at any one of these, then it's going to be either heating lot more or lot less. So a cheap way, and you can see that here. So the food in here, for example, uh, heats like that. Quite a bit, quite a bit of variation inside the food. So instead, if I just make the food rotate continuously, then it's going to see the highs, but it's also going to see the lows. So it'll kind of average out, smooth out. That's the idea of the turntable. This is a cheap solution to average out the non-uniformity that are fundamentally existing in the microwave oven. So the turntable rotates like this, and that rotation makes the food see high and low electric fields, as was already mentioned. So the food is going to rotate like that and see highs and lows. And as I said, this is an inexpensive way to decrease the non-uniformity. To have a comprehensive picture of how the turntable can make a difference in the electromagnetic energy deposition inside the food by the turntable, we turn to again electromagnetic simulation. This time we are back to simulation of a home oven, and in the home oven we have a cube, that's the food placed at the center of the turntable, and the cube is uh, of food analog, meat analog in this case, uh, made of tylose, and it has the properties of beef. And we do a full electromagnetic simulation, that is solving the Maxwell's equations inside the oven with the food in it. Details of this work can be seen in this published research. We now see the results from this simulation, and so here on the y-axis we have power absorbed uh, in watts per meter cube, or the energy absorbed, the power absorbed at any location inside the food, but it's not shown in watts per meter cube. It is scaled by a value uh, like the maximum value, and shown in a scale that makes it easier to see. Okay, and the x-axis is the various uh, orientations of the turntable. In other words, we do a full electromagnetic simulation, let's say at one orientation of the turntable, then we move the turntable and the food, and we do another electromagnetic simulation. So we do this starting from 0, the initial location, initial orientation, to all 360. The food, of course, rotates with the turntable. And what uh, we will see is the power absorption at one fixed location inside the food as it rotates with the turntable. First, we choose a location where consistently higher values of energy are deposited. So like here, this one here, um, But even for this location where consistently higher values of energy are deposited, you notice for some orientation of the turntable, it's actually lower than many other locations that we'll talk about in a second. So which means if the turntable did not rotate, then there is going to be great non-uniformities of energy deposition between, let's say, something at this orientation and something at the other orientation. But because the turntable rotates, it averages out this non-uniformity. So the hottest spot seems to vary particularly wildly. Now, if we look at another location where consistently less energy is deposited, so we call that cold spot because it will stay colder. So if we look at that one, then it stays consistently, let me use a different color, consistently lower levels of energy deposition. And it doesn't vary as much uh, like the one with the higher rates of energy deposition. We also look at other points like the one at the center or the top left corner, just another location, and we see variations. We see variations for the turntable orientation. The mean power is very interesting. The mean power is this one here. Uh, So the mean power really does not change that much, which is kind of what is expected. So the main point of for the turntable is that for any location in the food that would otherwise see high or low values to average out and the energy average out the energy absorption and thereby reduce the non-uniformity. Again, it sees average for some time, it sees high for some time and low for some time, and that averages out. At the end, there will still be locations that heat more and others that heat less, but the non-uniformity will not be as much with the turntable present. That's the main purpose of the turntable. Is another picture from the research work published here showing how turntable can make a difference. So the left picture is without turntable and the right picture is with turntable of a food surface, a rectangular food. After 35 seconds of heating, they show a very good qualitative description of the effect of turntable and how the right one looks more uniform. The rotating food on the right is more uniform. It still shows edge overheating and all that are characteristic of microwave heating, but it certainly looks more uniform than that one. And also the temperature scales are not the same. The value here is a lot lower than the maximum value here. So it is definitely looking more uniform. The middle region, on the other hand, it doesn't get affected as much since there's just no significant improvement of uniformity in the vertical direction. So the regions in the middle, they're not able to see many highs and lows because they're kind of not moving as much. If there were movement in the vertical direction, that would have seen perhaps more highs and lows. Again, a turntable then makes the food heat more uniformly. Here we try to quantify this non-uniformity that we have been talking about. And again, it's from the same research work, that is electromagnetic simulation of uh, heating of a rectangular block of food inside a home microwave oven placed on the turntable. So first, it's for the stationary situation, meaning the turntable is not rotating. Here is the mean temperature, and we want to show the non-uniformity, right? So we want to show kind of range. So what we have is this 10th percentile temperature, that's this line, 10th percentile. What that means is at this time, let's say 30 seconds, 10% of all the temperatures are below this value. 10% of the temperatures are below this value. Likewise, the other line, this one is 90th percentile, and so the meaning of it is 10% of all the temperatures are above this value. So the reason for doing this is to get rid of the extreme values, so that we're really extreme values like really hot or really cold regions, so that the non-uniformity we're talking about is a more reasonable representation of reality. So the spread between the 10th percentile and 90th percentile, this spread is a measure of a non-uniformity. It's a measure of non-uniformity. Okay, and that non-uniformity increases with time. Can you see that? And that makes sense because again, microwave heating is fundamentally non-uniform, so some places are being heated at much higher rate and some other places are at lower rate. So the temperature difference between them, between those two locations, would keep increasing with time. So this spread that you see here, how do you think this will change when we move from stationary food to a rotating food? Let's see. So here is a rotating food, meaning the turntable is now rotating. So let's look at 20 seconds. So at 20 seconds now, here is the measure of non-uniformity, so which is lower. No, lower, so non-uniformity is lower, and that was the purpose of the turntable. So we see that the spread of the temperature here increases here as well, but it increases less rapidly, meaning it stays more uniform than when not rotating. Finally, we look at the effect of power cycling as an oven factor in the energy absorption inside the food in a microwave oven. What is power cycling and why do we do it? Suppose you have a 700-watt oven, but you need to do half the power. You need to run it at low power, like 50% power, 350 watt. So when you set it for the lower power, 350 watt, what the oven really does is it heats at the 700 watt for half the time, so it's on for half the time, and the other half of the time for the cycle. So in this case it shows 22-minute cycle. The other half of the time the oven would be off, so that this half, it's called duty cycle, half multiplied by 700 is going to give us the 350 watt. Now, technology is available today that can give this 350 watt continuous like this, so it doesn't have to cycle. Now, the question is, there's claim by manufacturers of this technology that it does things better. uh, it gives better quality, like color, how the color develops would be better. What do you think is the rationale behind such a claim? How will the heating change, do you think? Will it reduce the non-uniformity in temperature in food? How will it affect the color that, let's say, darker color forms at higher temperature or for heating longer? So how would the dark color develop in either case, the cycling or the continuous power? You are welcome to pause the video and think about it a little. So coming back to the answer, the rationale for why the claim is made for better quality goes something like this. When there is cycling, when the microwaves are on here, when the microwaves are on, it is at a higher power. At the end of the heating portion of the cycle, right here, it is expected that the temperatures will be higher than if the power was continuous but at a lower value. Kind of obvious, right? Presumably then, for that moment here, at this 11 seconds, let's say, the quality change from heating would be higher than wanted, perhaps reducing the overall quality. That is the rationale, that the quality degradation could be more, or quality changes could be more for the cycling. But this is only momentarily. So once it reaches here, the heating stops and then the temperature reduces. The temperature reduces because the power is off, so the heat gets equilibrated, and so the temperature reduces a little, or doesn't go up as fast, is the better way to say. Let's check it out if that is the case. So we do a comprehensive simulation of the electromagnetics of a microwave oven heating that involves solving the equations for microwaves, the Maxwell's equations in the oven and in the cavity in the food. And the food is a cube as shown here, and the cube is a meat analog that has properties of beef, and we start from the frozen state. So we choose this corner or close to the corner temperature where for sure temperatures will be, we choose that corner where for sure the temperatures will be higher and therefore quality degradation can be quite significant. So we purposely choose this one that is more sensitive. So here you see this black line is the temperature at that corner location with time for the cycling condition. Because it's the cycling condition, you can see this kind of effect, that when it's off, the temperature in this location actually just cools a little. So you can see these irregularities in the temperature rise for the black one because it's for cycling on and off. But the red one is more smooth, and that's where we have the continuous heating, and one company refers to it as inverter heating. That's why we have the word inverter there. Um, so they are close. They're close. Since the average power is the same in either case, so it cannot hit too differently. Uh, but it seems our rationale was correct, that yes, things can be a little bit different, but the amount of change, the difference between the black and the red one for temperature now is minuscule, at least for this set of conditions. Now let's look at the color changes. That's this one here, lightness. So this color we are considering is lightness, that is assumed to follow a first order reaction, and it's going down with time. And so the color starts from some initial value like this one, and then it's going down with time. The black dashed line is for the cycling situation, and the red dashed line is for the continuous power. So again, you see there is some difference, right? For sure there's some difference, but the difference seems to be minuscule. So having cyclic power versus continuous power that is equivalent to the cycled power does not seem to make that much difference in temperature or the quality as we see here. Now let's dig into the process some more, and let's look at non-uniformity in the temperature for the two cases of cycled power and continuous power. So that is here. What is plotted here is the coefficient of variation. And what is coefficient of variation? It is the standard deviation of all the temperature values at any given time. So this is versus time. So at any given time, the standard deviation of all the temperature values divided by the mean temperature at that time. So that's what gives the coefficient of variation. So it's a measure of non-uniformity. So the non-uniformity initially increases as we start to heat. Why? Because microwave energy deposition is fundamentally non-uniform. So there are some places that energy is getting deposited at higher rate, which means the rate of temperature rise in those places are higher, which means the temperature difference between a place that has higher energy absorption versus lower energy absorption, the temperature is going to rise at two different rates. With the higher energy absorption place, the temperature rising faster. So temperature difference between two locations would keep increasing, which means the non-uniformity would keep increasing. Now diffusion increases with time, because as we just said, if the temperature differences increase with time, that will increase diffusion. Also, temperatures cannot go above boiling, so the non-uniformity uh, eventually drops. So what you see is that the red line for the continuous heating and the black line for cycled heating, they are not that different. So which means even the non-uniformity is kind of similar. So the conclusion is that cycled and continuous power gives about the same results. If you are interested in more details about this, you can follow up here in the complete research paper. Here now is a summary, not just of this video, but the series of 6 videos, of which this was the last one. They all dealt with the electromagnetic aspect of uh, microwave heating of food. The first one, we talked about and introduced electromagnetic waves. We said electromagnetic waves have electric field and magnetic field in them, and it's the electric field that's what really is doing the heating. And because microwaves are part of the electromagnetic spectrum, they follow the rules for other electromagnetic waves. And then we talked about uh, how the electromagnetic wave would behave not in a food in an oven, but in very simplified geometry, like in a very thick material with plane waves falling on them. Why did we do that? Because by doing that, we showed that the power of the wave can drop into the material as it's absorbed in an exponential way. But that was only for that specialized situation, not for oven heating. Now, the electric field of the microwaves interact with primarily two components, the water molecule and the ions, and this interaction uh, is characterized by two properties, dielectric constant and dielectric loss, and for foods they cover a very wide range. Then we talked about waves, this time inside an oven. And for any realistic microwave oven heating of food, the energy absorption is quite complex, and it varies spatially and with time. So inside an oven, the uh, the energy field distribution is quite complex because of formation of standing waves inside the oven. Microwave absorption in the food is related to many different food factors and oven factors, and also those factors are not uh, isolated. They are all coupled. Those effects are coupled. So what are some of these factors? So we talked about food factor in one video, and the food factors include, for example, shape, size, and aspect ratio, dielectric properties, and so on. And then we also talked about oven factors, and the oven factors include location in the oven, turntable, and power cycling. So we showed that the turntable, for example, can make a significant difference in the heating. So that concludes the part one of the microwave heating part of this food physics course. The part one talked about the electromagnetics. Now in the next set of videos, in part two, we will combine the electromagnetics with heat and mass transfer.